Welcome back. Let us resume our discussion on the overall digital control scheme that we have discussed. So far we have discussed the major component or the constituent of the control scheme, which is our ripple counter, and based on that we need to realize our overall control phases or the pulses which is going into different modules like the comparator, the ramping circuitry, sampling circuitry, offset cancellation circuitry, and so on. So based on the operation of the ripple counter, which is triggered by the main clock, we need to generate the other control phases. So if I look at the waveform that we are going to require, once again reverting to our two phases, phi 1, phi 2, and we are supposed to start the counting operation say at the negative phase of phi 1. So you may have the counter getting started over here, and we expect that the ramping voltage is also going to start at the negative edge of the phi 1. So you will have the V ref, which is basically the voltage stored on the capacitor, also ramping up at the phi 1 if at the phi 1 phase, and finally the point at which the V ref becomes equal to the sampled input, which is your V sample or V in sample. This is the red level denotes the level of the input data which is sampled, and the instance where the V ref becomes equal to the V sampled, I would like to have my transition. So at this point the comparator output will be changing. So we expect that the comparator output will be starting from high, and the moment this transition occurs, the comparator output will be going low, and this is the point who is there, who has brought the food? Twice it has been announced in the class. Who is there? Your notice is not visible in the class. It has been announced twice. Now let us continue the discussion. Don't worry, this will be off the record. So, but it is not, if you are not taking seriously, these are your other classes are there, other people will be coming, and if you are leaving these things behind, last several classes the same thing is happening. We have told you before also, but again you are leaving the packets and all the food item on the chair. So they are not supposed to do the cleaning for you, right? They are the staffs who are helping you in coordinating this lecture. So it is not their work to clean for you. So you are unnecessarily creating issues here. Okay, so let us resume our discussion. So what I want is the comparator output will be going low at this point, and accordingly you will have the data or the counter output to be or the recorded or registered at this point. So whenever the comparator output is going down, I would like the counter output to be registered as my final data for this particular conversion duration. And finally at this instance, once again I have to create the phi 1 pulse. So that these are the operations that I need to do. I need to detect this transition time, and at this point only whatever counter output is coming, I need to latch it to circuitry or a latch which is storing my digital output for this conversion cycle, and then at the end once again I have to make sure that the phi 1 phase is going up. So based on the counter scheme that we have, how do we implement these operations? So let us see the first operation where we need to identify the transition point and make sure that the data is made available, whatever counter output is available till this point, it is transferred to a set of registers and that is made available as the output digital word for this particular conversion cycle. So, this is one particular conversion cycle. After the phi 1 comes again, next cycle begins. So, in this cycle the conversion is happening on the particular sample data that is available over here. In the next cycle, once again the sample data may change, right. So, you have in the phi 2 phase the sample data may change to a new value and you have some other V in, and therefore, the conversion cycle will again begin when the phi 1 goes low, and once again you will have the same slope for VREF climbing. At some point it will meet, and once again you need to register the data. So, this is the overall operation, and for that I can use another set of flip flops which are supposed to store the data or the counter output when this transition happens, and the control signal for that particular set of flip flop can come from the comparator. So, you see the comparator output transitions over here from high to low, and once again during the phi 1 phase when the data is getting sampled and the reference signal has been discharged to 0, it will be once again transitioning to low to high. So, remember the comparator output, it is remaining is going to remain 0 till the reference voltage is once again brought down. How does the reference voltage is brought down? We remember that we have a discharge switch also, which is shorting the sampling or the C ref, which is basically storing this sampling or sorry the reference voltage. So, we have the reference C ref, and of course, you have the I charge that we have implemented using current source, and you have the switch over here which is operated in phi 2 phase which charges this capacitor, and also whenever the phi 1 phase comes you have the other switch which is supposed to discharge this. So, whenever phi 1 is coming over here the VREF is again discharged to 0, and as a result the comparator output will once again be turning high, because this is 0 and V in range of course is going to be slightly higher than 0, minimum value will be V over drive. So, V in will be slightly higher than 0 in this period. As a result, I can assume that the comparator will be making a low to high transition back at this point. It will have some delay of course, the moment in the phi 2 phase, the moment this is discharged to 0, it will have some delay, but roughly in this period the comparator transitions again, and once again it will remain high for the entire duration, and once again in the next cycle whenever the capacitor voltage is crossing the sampled voltage, once again the comparator will be making a transition. So, whenever the high to low transition in the comparator happens, I would like to register or record the counter output. Therefore, I can have a set of flip flops which are taking the counter output as input data, and their clock can be set to the comparator output. Whenever comparator is transitioning from high to low, that negative edge should trigger the registering of the data or registering of the counter output into the other set of flip flops. So, that is a scheme I can implement. So, effectively if I try to see this, you have the original counters flip flops, you have the original counter flip flops. I am not drawing all the connections. You have say Q1, Q2, Q3, Q4, and these outputs are available to you. In this case, we have a ripple counter, and therefore, the main clock is coming only to the first one, and we know that you have the connectivity from the Q1 to the clock of the other ones, and so on. And we have the comparator output. I can have another set of flip flops which are taking these flip flop outputs and their clocks, they are once again negative edge triggered, and their clock is coming from the comparator. And finally, I have Q1 dash, Q2 dash, Q3 dash, and Q7 dash 8 dash basically, sorry 7. So, this is the scheme that we are going to have, and these are my final outputs Q1 dash, Q2 dash, Q3 dash and Q7 dash, which is available as the digital word for that particular cycle. So, in one conversion cycle, these Q1 dash to Q7 dash will be changing their state only when the comparator is having high to low transition, and then it will be registering the data for that cycle. Next, it will change only in the next conversion phase, in the next conversion cycle, and therefore, at the rising edge of the phi 1, I can use this data for my digital processing, because just before the rising edge of the phi 1, I am entering into the just after the phi 1 phase, I am entering into the next conversion cycle. So, before that I can take this data stored in this register, these 7 bits, into my digital domain. You will have another set of registers, or you have some logic blocks in the digital domain, which are going to use this data and process it further. So, those digital blocks can be triggered with the positive edge of clock over here, and they will be taking the new output or the new digital word corresponding to the last conversion cycle, say at the positive edge of phi 1. So, the overall ADC output available as the 7 bit word, this is your output data, and this denotes bits. So, when we have this cross, it denotes n number of bits. If I denote this number, that means 7 bit data, and that is going to the digital block, where you can have the very first stage as another set of flip flops, which are having 7 flip flops, and all of them are triggered by the same clock, which is having a rising edge over here. Then onward, it enters into digital domain, and rest of the processing happens in the digital domain. You have a bunch of computation going on, arithmetic computation and going on, and all that processing going on over here. So, this is regarding the registering of the data, right. So, at what instance we are registering the data and transferring into the digital domain. Now, of course, the other thing we also need to look into is the generation of these phi 1 pulses from this original clock. So, in general, as I said, in the system you will have a single global clock, and based on that clock you will be generating this phi 1 and phi 2 phases. So, how to use this single global clock to generate this phi 1 and phi 2 phases, and also what do we need to do to this counter, which is taking this main clock as the input. So, what happens to the Q1, Q2 up to Q7 when the final value, say 1 1 1 is being reached, and then subsequent to that, how do we generate these two control pulses phi 1 and phi 2. So, if we just go back to our original truth tables that we have, and if you look at negative edge, any instance where all the flip flops have been turned 1. Suppose I am drawing an instance, a particular negative edge close after which all the outputs have been transitioned to 1. So, I am just consider this as a separate case, different from what is drawn in the above waveform. If all the outputs have gone high at this positive edge, what happens at the at this negative edge, what happens to the outputs at the next negative edge, because we are following a sequence, right. So, starting from 0 0 0, you have 1 0, then you have 0 1, then you have 1 1, and so on coming in. So, if I look at this waveform, this is the sequence going to follow till the MSB 0 0 0, 1 0 0, 0 1 0. So, likewise 2 3 and so on is going to increase, and finally, all the bits will be becoming 1. There will be a clock cycle for which at the negative transition all the flip flop output will be turning 1. So, after that, of course, what is the scenario? All of them are going to toggle at the next positive edge simultaneously from 1 to 0, because at before that edge all of them were 1, and at the next positive edge at the next negative edge all of them are supposed to toggle from 1 to 0, and therefore, at this instance all of them will be automatically transitioning to 0, and again the cycle will start. So, all of them again getting reset to 0 after reaching 1 1 1 1 1, and again starting afresh from 0 0 0 0. That is automatically happening. We do not need to apply any additional control to do that. So, if you allow it to reach the maximum value 1 1 1 1 1, After that, the next phase, of course, all of them were 1 just before the negative edge over here. Immediately after that, all of them will be transitioning to 0. So, this is the operation we expect, and therefore, if we simply allow the counter to run, if we simply allow these flip flops to keep running and keep counting till the maximum value 1 1 1 1 1, after that anyway all of them will be transitioning to 0, and that is going to give me the control signal for phi 1, means when should I set the phi 1 high. So, that should happen when once again all of these are making a 1 to 0 transition, from all of them have reached 1 and then they are making 0. Once again I should activate phi 1 and start afresh. So, how can I do that? So, if I look at the waveform once again, and this is the main clock, which is the high frequency clock, and these are the output of the flip flops, individual flip flops. And likewise, you may be having any certain output, so that at a certain instance you are having all of them turning to 0. So, you will have a certain instance where all of them are turning to 0. And so on, and this is the duration at which the conversion cycle stops or ends. So, here at this negative edge, all of them after reaching 1 1 1 they are transitioning to 0 at the particular negative edge over here. So, how do I generate the phi 2 pulse? So, here after the next negative edge over here, once again I would like to start counting. So, we can have the phi 2 pulse, for example, generated during this instance, and here what we can do is, in order to generate the phi 2 pulse, we see a clear logic. What is the logic we need to implement? So, here the clock, the main clock is low and all others are also low, and therefore, simply using the AND operation of all these Q1 bar, Q2 bar, Q3 bar, Qn bar and the main clock bar, I can generate a phi 1 pulse. So, whenever all of them have turned low and at the same time the clock is low, I can use that as the phi 1 pulse. And so, therefore, if I use this logic, this is nothing else but phi 1 is equal to Q1 bar dot Q2 bar dot Q3 bar Q7 bar dot CLK bar. So, whenever this logic is going high, I can transition to the phi 1 phase, and during this phi 1 phase I should make sure that the sampling is happening properly, the sampling speed is good enough, the switching the switches that you are using in the sampling is able to charge the sampling capacitor. At the same time, you are having the discharge switch also phi 1. So, during that phi 1 phase, we have to make sure that this switch is able to discharge the Cref. During the sampling phase, we also have to make sure that the input data is getting sampled appropriately on the sampling capacitor, and also we have the other circuitry where you have the offset cancellation going on, or sampling of the offset going on the offset capacitor or C offset that we discussed yesterday. So, these three operations need to be finished within this phi 1 phase. So, the Cref needs to be discharged, the input data needs to be sampled, and the offset of the amplifier also needs to be sampled on the C offset, and all these three should be fast enough so that they can be completed within this duration. That is something we have to make sure, and you might have noticed in the simulations also. So, the choice of the Cref over here and the corresponding switch dimensions over here become critical when we are trying to do the discharge operation. So, this one is relatively simple. This constraint of discharging this capacitor to ground is relatively simple. Only thing you need to do is make this switch large enough, so that within the phi 1 duration, it is comfortably able to discharge. If you make it minimum size and this capacitor is large, say we have taken pretty large capacitor just to allow lower current, if you remember, sufficient current, if you remember, this capacitor was chosen as 20 picofarad around, and therefore if you use a minimum size switch, the RC time constant may be too large and it may not allow it to discharge completely to ground during the phi 1 phase. So all you need to do is make this switch large enough. Here of course, when we make the switch large, we know that we are going to have leakage flowing through the switch, and the leakage component can once again disturb the stored charge, but this is not a floating node. You are having the current coming over here, and here we are not really, even if you make this sufficiently large and during the off phase we are having some leakage component over here, that leakage component also will vary as this voltage is changing, but that leakage component can be of the order of say few tenths of nanoampere. If I keep this leakage component sufficiently small as compared to the charging current, say at least 100 nanoampere, then still the slope may not change significantly. So there comes the trade off. You have to be careful while designing this charging circuitry that we need to make the slope constant, right, and in order to make the slope constant, we are using this constant current source, and we try to so we looked at the constant current source, and we tried to keep this sufficiently large so that we are able to have a current of around 0.1 microampere. If we go for smaller capacitance, then the current required will be further lower and it will be less reliable. So that was the reason why we chose such a large capacitor of 20 picofarad. And if we choose a large capacitor, we also need to choose a sufficiently large switch over here, which is able to discharge that capacitor during that narrow phi 1 phase, and then we also going to have more leakage over here. So when phi 1 gets off, that leakage is again going to cause deviation from the required value, and this leakage current is not constant. As the voltage increases over here, leakage will increase. As a result, it can lead to non-linearity, and as a result you can have some inaccuracy. So you have to make sure that if you are choosing a large capacitor corresponding to a large switch over here, and then during the charge phase you are trying to charge it with a small current, the leakage is sufficiently small so that it does not really make the slope deviate from the constant value we want. That is the concern you should take care of. So here the simple thing is, make the switch large enough so that it discharges fast during the narrow phi 1 phase. Make sure that during the off phase of this phi 1 or in phi 2 phase, the leakage current through the switch is not too large, so that it starts, the voltage over here, the slope of the voltage here starts deviating from the constant slope we want. So that is the cross check you should have for this case. Of course, for the other two circuitry, the sampling circuitry, we have to look at the sizing of the switches. As we saw in the sampling circuitry, the sampling switch size is going to determine the RC time constant, and we calculated that the minimum size transistor was also expectedly meeting our RC time constant quite comfortably. So there the switch sizing was not very critical, provided we are using few picofarad of sampling capacitor. And if you remember our circuitry for the offset cancellation, there also we had the C offset, which is supposed to be charged with V offset using the closed loop unity gain feedback. And during that duration, once again for the unity gain amplifier circuit, the C offset acts like a load capacitor, and during that duration the unity gain amplifier should be able to charge that load capacitor. And in other words, the transient response of the unity gain feedback should be fast enough so that during that phi 1 phase it is able to charge the load capacitor or the C offset with the required offset voltage, and it is able to settle during that duration. That will require that the bandwidth of the closed loop unity gain amplifier constructed with the same comparator is higher than the bandwidth given by this period. So that is another constraint that we have. So these are the issues we need to take care of while using this phi 2 phase. So basically we can just simply send this phi 2 phase to the phi 1 phase to the three switches that we have, the discharge switch over here, the sampling switch, and the offset cancellation switch, and of course the phi 1 the phi 2 phase goes to the current charging switch over here, and the input sampling switch for the comparator that we discussed. Here phi 1 we can of course adjust. If you want the phi 1 to be longer, we can make it longer, then the logic required over here will be different. Here the logic implemented is simpler. You are just ANDing all this Q1 bar, Q2 bar up to clock bar. If you want the phi 1 to be longer, then you need to make sure that the counter is disabled for longer duration. It is not counting for a longer duration, and also you need to have another scheme which is going to count how many pulses of phi 1 you want for the, or how many phases of the clock you want for the phi 1 duration. For example, when the phi 1 goes high, after that logically what should I do in order to extend the phi 1 further? I should count how many clock pulses of the original waveform you need for phi 1 to be high. So, if I want to extend phi 1, right. So, one of the question was that, okay, if you want to keep phi 1 high and you want to have the sampling duration slightly longer, so that the RC time constant is relaxed, and also on the other hand your comparators closed loop operation can be relatively slower. So, there I can extend the phi 1. Remember, phi 1 is putting constraint on the closed loop operation of the offset cancellation circuitry. If you remember the offset cancellation circuitry, that can be having a severe constraint, as we discussed yesterday. So, you are having the sampling capacitor coming over here, and in the unity gain configuration, this is the effective circuitry we are having. You are connecting this to VCM, so effectively AC ground, and this is the C offset, and this is your V out. So, effectively for V out, C offset was appearing as a load capacitance, and we are doing it in the phi 1 phase. So, we are operating these 3 switches in the phi 1 phase, and therefore, we should make sure that during this small duration, the phi 1 phase, it is able to charge this C offset to the required V offset. Therefore, the settling time should be fast enough, and we have seen earlier also settling time depends upon the pole of the amplifier, the 3 dB cutoff frequency of this closed loop operation, and we therefore should make sure that the closed loop bandwidth of this unity gain configuration is fast enough as compared to the frequency given by this phi 1 duration. So, if you keep phi 1 equal to this low duration of the clock, low phase of the clock, the corresponding period that we see, of course, is going to be almost twice the clock frequency. So, the bandwidth of this comparator should be several times higher than twice the original clock frequency, so that the settling is fast. So, that will be the constraint. So, if the frequency over here is 250 kilohertz, I would like the closed loop bandwidth to be several times higher than that, at least say a megahertz will be a comfortable number. So, that was the constraint. If I allow this phi 1 to stretch longer, so for longer duration phi 1 is staying high, then of course, I will be able to allow more time for the phi 1 phase, and therefore, I will be able to allow more time for this closed loop unity gain configuration to charge the C offset. Likewise, I will be able to allow more time for the sampling capacitor, where the input is getting sampled on the sampling capacitor. We have seen, however, that is not a very severe constraint. Even if you are using this low duration, for example, having 250 kilohertz of clock, and you are using this 4 microsecond of duration for sampling the data onto the sampling capacitor using the switches, even minimum size switch would be able to meet that constraint. You can slightly increase the switch dimension, of course, to meet that. That is not a, there is a relatively less severe constraint, but here the constraint can be more critical, because here you need to make sure that the open loop bandwidth of the amplifier is close to 1 megahertz, despite the large load capacitance and the compensation capacitance coming into picture. So, that was more serious constraint that we discussed in the last class. So, this constraint may mandate that, okay, rather than trying to push this closed loop bandwidth to higher value, I can extend this phi 1 duration a little longer, so that I can relax the bandwidth requirement for the closed loop operation. What we discussed yesterday, that open loop bandwidth, you do not have the compensation capacitor, you do not have the stability constraint. So, that is not a major constraint, you are easily able to achieve the open loop bandwidth, but for the closed loop bandwidth we have effectively this large C off coming, that loads the capacitor, loads the comparator in the closed loop. As a result, you have to use the compensation capacitor, and as a result the bandwidth goes down, and in order to make sure that the bandwidth is remaining sufficiently high, I would like to stretch this. So, this question is clear. Like we first looked at the simpler scheme when we are assuming that okay, just one duration is good enough for achieving the phi 1 pulse, and during this phi 1 operation, all these three operations of offset sampling, input sampling, we have the input, this is your phi 2 phase, and at this point you have the input getting sampled. So, if I mark this as a star, you have the input getting sampled as well. So, this is the star point. This switch is off during phi 1, on during phi 2, others are phi 1, phi 1, phi 1. So, this is also happening during phi 1 phase of the sampling capacitor Cs. So, this sampling of the input, the offset sampling on C offset, and the discharge of the C ref, all these three should complete within phi 1, and what we identified is the more critical one can be this closed loop operation. Other two are easier to solve. Probably here you just need to take care of the leakage in the off state, otherwise you can just increase the size, just have a cross check that the leakage in the offset is not disturbing the C ref or making it non-linear. That is one constraint, and the other one, this is also relatively easier to handle. If you just for instance increase the size of the switch a little bit, or corresponding to that, just to preserve the same voltage level and signal integrity, you increase the Cs, so that leakage is not causing the droop. So, this is also relatively straightforward, but the constraint comes here. So, for that we can discuss another extension where you can try to make this phi 1 programmable, or you can have a longer duration for phi 1. Any question? So, this distinction is clear between the present scheme where we are using only one negative phase of the clock to generate this phi 1 simply by taking the AND of all these outputs, and second one where we would like to extend this phi 1 for longer duration.
Can you make it shorter?
Shorter will not be feasible, because here the transitions, the fastest transition will be allowed by the fastest clock that you have in the system. You can make it shorter, you can some logic, you can insert some logic, whether rather than clock, if you want to rely on some logic, you can do that, but why will we do that? That is not required at all. It is not going to give us any benefit in terms of functionality or speeding of the operation. There is no point. So, we can take a 2 minutes break and then resume our discussion. We can discuss the alternate scheme and then go into the transistor level implementation of all these blocks, the flip flops, the logic that we are trying to implement and everything, and look at the issues related to transistor level implementation of these circuits.